Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about the problem of multicollinearity and how to detect this particular problem using a technique of VIF, or the variance inflation factor. Even before I proceed to demonstrate how to check for the problem of multicollinearity, may I request you to subscribe to my channel, also like and share my videos. Firstly, what exactly do we mean by multicollinearity? Remember, one of the important assumptions in linear regression is that the independent variables are uncorrelated. I repeat, one of the important assumptions in linear regression is that the independent variables are uncorrelated. Now, the question is, what happens when the independent variables violate this assumption? Or, in other words, what happens when the independent variables are highly correlated? When the independent variables are highly correlated, that's when we get the problem of multicollinearity. So in simple layman's terms, multicollinearity is a problem that arises because of high correlation between the independent variables when we build a linear regression model. Now that we have understood the problem of multicollinearity, the next question is, how do we detect the problem of multicollinearity? There are many ways in which you can detect for the problem of multicollinearity. In this video, I would like to talk about one special metric which is called as VIF. VIF stands for variance inflation factor. Typically, if the VIF or variance inflation factor is greater than 4, it indicates multicollinearity. If the variance inflation factor is greater than 10, it indicates serious multicollinearity in the data set. Now, you may ask me, why should I care about multicollinearity? And how does multicollinearity affect regression? I repeat, how does multicollinearity affect regression? The answer is very simple. Multicollinearity affects regression in 4 ways. Firstly, when we have multicollinearity, the standard error will shoot up. Secondly, the p-value that we obtain will be unreliable. Thirdly, multicollinearity weakens the statistical power of the regression model. And fourthly, the coefficients will be unreliable. I repeat, the coefficients will be unreliable. So these are the 4 problems that we get because of multicollinearity: high standard error, unreliable p-value. We will have a very weak statistical power of the regression model, and finally we will have unreliable model coefficients. These are the 4 important consequences of having a high multicollinearity. Now, to demonstrate how to detect multicollinearity, I'm going to use a data set which is called as the Boston housing data set. By the way, this is StatCraft software. This is a Make in India initiative. It's a very useful and a powerful software. I'm going to use this to show you the impact of multicollinearity. First of all, to load the data set, I can choose the view button. Then I'm going to go to tables. Let me scroll to the last row here. You can see here, StatCraft shows a data set which is called as Boston. This is the file which I'm going to work on. You're probably familiar with this particular data set. I have used this, I have loaded this data set from Kaggle. The very useful variables like crime rate, ZN, Indus, CHAS, nitric oxide concentration in air. You also have the average room size, age, distance, the variable radius, tax. You have pupil to teacher ratio, the number of blacks, proportion of lowest status of population, and lastly, you have the median value of housing price. So what we have is basically the estimated median value of homes, different homes in Boston. And along with the estimated median value of homes, they have also given us nitric oxide concentration in the air, the number of rooms in the house, the proportion of blacks, the proportion of lowest strata of population. I propose to use the last variable, median value, as the dependent variable. The rest of the variables can be used as the independent variables to construct a predictive model. Firstly, let's do some exploratory data analysis to check the extent of correlation that is present in the data set. Let me click on the analysis tab, scroll down. You can see the option graphics. We further scroll down. There are different graphs here like scatter plot, bar plot, box plot, so on and so forth. I'm going to scroll down and choose the option called as Correlogram. Correlogram gives me the correlation matrix. This can be used to tell which variables have high relationship. And when these variables have high relationship, rest assured that there is the problem of multicollinearity. So let me choose Correlogram. You can see here, there are different variables like crime rate, ZN, Indus, CHAS, nitric oxide concentration, rooms, age, distance, the variable radius, tax, PT ratio, black, LSTAT. I'm not going to choose the median value of home because this variable will be used as the dependent variable. The rest of the variables are all my independent variables. I have pushed all my independent variables into the analysis tab. Let me go to options. I'm going to increase the size for better visibility of the text. Color, yes, I want a correlation plot with the coefficients. I have to enable this. So let me enable the correlation value. So I'm going to change the color here. Let me go ahead and hit OK. What the Correlogram does is it gives you the correlation matrix. This is the very first step of analysis wherein we are performing the EDA or exploratory data analysis. So this is how the correlation matrix looks like. Let me zoom it in for better visibility. As you can see here, there are different variables that we can see. You can see a whole lot of variables along the row as well as the column. The blue circles indicate positive correlation. The red circles indicate negative correlation. Larger the blue circle, more the correlation, and smaller the circle, lower is the magnitude of correlation. So let me draw your attention to some of the big circles here. Clearly, you can see a large circle here, namely, this is a large circle here. This is the correlation value between the variables Indus and nitric oxide. The value of correlation is 0.76. Anything greater than 0.7, we can say that there is a high magnitude of correlation. So clearly, we have identified the first culprit variables, that is nitric oxide concentration and Indus variable, because these two variables have high degree of correlation, implying that these variables could potentially cause multicollinearity. Similarly, let me draw your attention to 0.76. This is again the relationship between nitric oxide and the variable Indus. So again, there is a high degree of correlation between nitric oxide concentration and Indus. This might cause severe problem of multicollinearity. When I scroll further, you can see 0.73. This is the correlation between the variable age, and when I scroll up, you can see nitric oxide concentration. So nitric oxide concentration is recurring again and again. It seems to be correlated with a lot of variables. Let me scroll further down. I see a high value of correlation here. In fact, this is 0.91. My apologies in case you're not able to read this number. This is 0.91. This is the correlation value between the variable tax and the variable radius. So 0.91 is clearly greater than 0.7, indicating that there is a high degree of correlation between these two variables. So what we have done at this stage is to perform the Correlogram, and using the Correlogram, we are able to identify which set of variables have relationship. In our data set, there are a lot of variables which demonstrate interrelationship, and therefore we can expect the problem of multicollinearity in the data set. Now, this is a very, very rudimentary way of identifying correlation. Is there a more refined way of identifying correlation? Let me talk about this in the second step. I'm going to click on the view button and then go to data. Here I've got my data set. This is the data set which we are working on. Now, in the second step, let me go ahead and perform regression. I have just now clicked on the analysis tab. This is the regression option. Let me click on the drop-down menu and scroll down. You can see here, the second item here is linear regression. I'm going to choose the option linear regression. Here, I'm expected to specify the dependent variable as well as the independent variable. Remember, the last variable, namely median value of the housing price, is my dependent variable. The rest of the variables are my independent variables. Let me choose some of the variables like crime rate, ZN, Indus, CHAS, NOx, RM, or the number of rooms, age variable, distance, radius, tax variable, PT ratio, black, LSTAT. All these are my independent variables. Though you can do a lot of things with regression, I'm just interested in showing you one of the important options, namely VIF, or variance inflation factor. Now, variance inflation factor is a way in which you can detect multicollinearity. Now, you may ask me, how is VIF calculated? There's a simple formula. VIF equals 1 divided by 1 minus R square. R square is nothing but the coefficient of determination. How can you tell whether there is multicollinearity from VIF? If VIF equals 1, then you're safe. Your data does not have multicollinearity. I repeat, if VIF is exactly equal to 1, then you're pretty safe. There is no multicollinearity. On the other hand, if VIF is bigger than 4, then it means that there is moderate level of multicollinearity. I'm going to click VIF and then hit the OK button. Let me scroll down. You are going to see a lot of information that's printed out, like the model summary table, the coefficients table. I will not be looking at this stage. I'm interested in drawing your attention to VIF. Let's watch out for this table. Against each independent variable, StatGraph displays the VIF. So the first variable crime has a VIF 1.79. It is less than 4, so you're safe with this variable. ZN has a VIF of 2 point something, less than 4, so we are safe. Indus has a value of 3.99, very close to 4, but it is less than 4, so I will ignore this. The variable Charles River is 1.07, less than 4, so we are safe with this. But look at the variable NOx. It is 4.3. Clearly, this has violated the thumb rule. The thumb rule is that if the VIF is less than 4, only then you can say that there is no multicollinearity. Because the NOx value is greater than 4, it means that we have the variable NOx is contributing to the problem of multicollinearity. The variable RM, age, that is the room's age, distance, all of them look to be okay because it is less than 4. But I again have a problem with the variable radius. It is 7.4, clearly greater than 4. Look at the variable tax. It is greater than 4, right? So the variable tax, the variable radius, and the variable NOx, these are the 3 variables which are causing multicollinearity. Why do I say this? Why do I say this? I say this because they are violating the thumb rule of VIF less than 4. If VIF is greater than 4, then we can say that there is the problem of multicollinearity. So now that we have come to the conclusion that there is the problem of multicollinearity, largely triggered by variables like NOx, tax variable, and radius variable, what do we do about this? How do we rectify the problem of multicollinearity? To solve the problem of multicollinearity, there are different measures. These days, people talk about regularization techniques, where they popularly talk about L1 regularization as well as L2 regularization to remove the problem of multicollinearity. There is a simpler solution, and it is a pretty old solution, which is to use the independent variables and perform principal components. Once you perform principal components, generate the principal component scores. And the important property of the principal components is that they will be uncorrelated. Once you get uncorrelated principal components, you can go ahead and use them as the independent variables in the regression model and build your regression equation from that. So the next step, which is the third step, is to perform the PCA. So let me go to the option data. This displays the data set. We have established that there is the problem of multicollinearity, and therefore to rectify the problem of multicollinearity, I'm going to perform principal component analysis on my independent variables to remove the problem of multicollinearity. Let me click on the analysis tab, scroll down. You can see dimensionalities. Here you see different options like factor, PCA, and linear discriminant analysis. I'm not interested in factor analysis. I'll do a PCA. The PCA will be done on the independent variables. Under the variables option, crime rate, Zn, indus, CAS, nitric oxide, rooms, age, distance, radius, tax variable, PT ratio, black, and LSTAT. I'm not going to use the dependent variable medley. So these are the 13 variables that I will be using to perform the PCA. The number of factors here, I'm assuming, would be 3. Since this is exploratory factor analysis, I'm starting off with 3. How do we decide the optimal number of factors? This is the most important question in PCA. To answer that question, there is what is called as the Kaiser criteria or the K1 criteria. Kaiser proposed a criteria which says that if the eigenvalue is greater than 1, extract those many components. So I'm going to go with the same idea here. Let me choose rotation and Varimax rotation. In options, I'm not going to choose, okay, I can click on the eigenvalue method and choose the plot. Under the plot, I can choose what is called as the scree plot. I'm going to look at the scree plot to decide what is the optimal number of components in the data set. Let me go ahead and hit the OK button. Let me scroll down. StatCraft prints a lot of output. Don't worry about all of these tables that you see. We have to just worry about one important table, which is called as the eigenvalue table. What is the thumb rule here? If the eigenvalue is bigger than 1, extract it. If the eigenvalue is smaller than 1, ignore it. You can see here, the first component has an eigenvalue of 6.1, clearly greater than 1. You can go ahead and extract the first component. The second component has an eigenvalue of 1.43, again greater than 1. So you can go ahead and extract it. The third component has an eigenvalue of 1.24, greater than 1. So you can extract the third component as well. So when you look at the fourth component, this is where the problem starts. When you look at the fourth component, the eigenvalue is 0.85. This is not greater than 1. This is less than 1. Subsequently, all of the components, 5th, 6th, 7th, 8th, 9th, 10th, all of these components have an eigenvalue smaller than 1. You can clearly see here the eigenvalue is 0 point something. So since 0 point something is less than 1, we can draw a line here and say, in our data set, we can go ahead and extract 3 components. I repeat, 3 component solution is optimal for this data set. So this is the K1 criteria. Along with the K1 criteria or the Kaiser criteria, you can also look at additional criteria, which is called as the scree plot. This is the scree plot that you can see here. And the y-axis, what you're seeing is the eigenvalue of the factors and components. So this is nothing but the eigenvalue. And in the x-axis, what you're seeing is, let me show you the x-axis in a bit. You can see here in the x-axis, we have the factor or the component number. So this is the cutoff. So this is what is called as the Kettle's scree test. The Kettle's scree test says that look at the elbow of the graph or the bend, or sometimes is also popularly called as the inflection point. So against each component, you have the eigenvalue. So against the first one, you have an eigenvalue of 6 point something, clearly very, very high. Then you can see there's a sharp dip in the eigenvalue for the second component. It drops sharply. For the third component, it further drops. And for the fourth one, you can see here, it is less than 1. So this portion of the curve clearly flattens out and we don't have to look at this. So this itself, you can consider as the inflection point. You can consider this as perhaps the second inflection point. This is the first inflection point. So since there is a sharp dip in the eigenvalue less than 1, you can clearly ignore the subsequent components and you can look at only the first 3 components as per the scree plot, which is consistent with the eigenvalue method that we looked at earlier. So what is the conclusion? The conclusion is that we are going to extract 3 components. So let me go to view and then choose data. Right now, after performing PCA, we have come to the conclusion that there are 3 components in the data set. So let me go to analyze, scroll down, choose the option dimensions. I'll click on PCA. This is what we had done earlier. Everything remains the same. The one thing that I need to do additionally is I have to save the principal components. So I'm just clicking on the save button and principal components. So what this does is it will create 3 new variables in my data set. It will create 3 additional variables. I'm going to hit the OK button. Let me go back to data. Right, let me scroll to the extreme right side. You can see here, I had variable till medv. Now I have RC1, rotated component 2, rotated component 1, and rotated component 3. So these 3 are the output of PCA. We are going to use the output of PCA as the input for regression. I repeat, the output of PCA will act like the input of regression. Why am I going to choose these 3 variables? Because these 3 variables are uncorrelated. So for further analysis, you can just use these 3 variables. You don't have to use the 13 independent variables. The 13 independent variables suffered from the problem of multicollinearity. These 3 new variables that we have created do not have the problem of multicollinearity. So for any advanced analysis, you can go ahead and use only 3 variables, only 3 variables. What is the advantage? The advantage is that working with fewer number of variables is always a lot easier than working with a lot of correlated variables. So to summarize, we have created 3 new variables, which I'm going to use as the input variables for the rest of the method. So let me again go to analyze. Now I need to choose the option regression. Let me click on the drop-down menu. You have linear regression. This is my linear regression method. You can see here, all these are my old variables. I can just refresh this. I don't need to use 13 variables. I'm going to use only 3 variables. My dependent variable will be the same medv. And now, when you look at the independent variables, RC2, RC1, and RC3. Let me choose the option. Here, I want to show the VIF value here. And then you can choose the variable importance if you want. Plot, I'm not interested in any plot. If you want, you can choose the fitted value as the residuals. I'm going to ignore this and hit the OK button. StatCraft has executed the linear regression model, and you can see here the output that StatCraft gives us in the output window. Though it gives a lot of output, I'm interested in going to the last table, which is the VIF table. Please look at the VIF here. The VIF for the three components is 1, right? So the VIF is 1 here. So congratulations. Since the VIF equals 1, this is a breakthrough. VIF equals 1 means that there is no multicollinearity in the data set. I repeat, since the VIF that we have got is 1, it means that there is no multicollinearity in the data set, and the variables are completely independent of each other. So this is the beauty of using the PCA. The PCA generates principal components, and these principal components are completely uncorrelated. So we've been able to solve the problem of multicollinearity by using the technique of PCA. Let me draw your attention to the earlier regression output. So this is the earlier regression output that we had obtained when we used 13 variables. Is this the one? It looks like this is the one. Remember, this is the VIF that we got. For the original variables, we said that there are many variables wherein the VIF is greater than 4, which is a real big problem. NOx, for example, violated our thumb rule of greater than 4. It has a high VIF. Similarly, when you scroll down, you can see here tax variable is 9 point something, high VIF, a big problem. The variable radius 7.4, high VIF, which is a problem. Since at least 3 variables violated the thumb rule of high VIF, we had to do a PCA. Now that we have done the PCA, what is the result? Let me click on the VIF. This is not the output that we were looking at. This is the variable importance. Let me scroll up. You can see here the VIF is exactly 1, which means that the problem of multicollinearity is solved. Let me quickly go over the regression output. This is the variable importance table. So rotated component 2, its importance is 11, but I would like to draw your attention to rotated component 3, which has a high overall importance of 25. So one of the variables which drives the housing price seems to be component number 3, followed by component number 2, and then we have component number 1. What is the R square for this model? You can see here. R square is 63.63 rather. So 63% of the variation in the housing price for Boston houses is explained by the set of independent variables that I have, which is good. You can see the 3 variables, their estimates are all negative. You can rely on these estimates because they're completely independent of each other. The standard errors are also on the lower side. Look at the p-value here. Each of these p-value is less than 0.05. It is very, very tiny. Now, since this is very, very tiny, you can go ahead and say that since the p-value is very, very less, you can reject your null hypothesis and say that each of these variables and their coefficients we have to take seriously, right? So the model coefficients are significant, and to construct the regression equation, we will be using these 3 variables. So to sum up what we discussed, when the independent variables are correlated, it leads to the problem of multicollinearity. Next point is, how do we detect the problem of multicollinearity? We can detect the problem of multicollinearity by looking at the VIF value. VIF equals 1 indicates no multicollinearity. If the VIF is greater than 4, it indicates moderate levels of multicollinearity. There's a lot of literature which claims that if the VIF is greater than 10, only then we take it seriously. How does multicollinearity affect a regression model? This is a very good interview question as well as an examination question. If you have multicollinearity, the standard error will be inflated. The p-value that you get will be unreliable. Multicollinearity weakens the statistical power of the regression model. And finally, the coefficients will be unreliable. These are certain consequences of multicollinearity problem. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much. Have a great day ahead.